All right, guys. So this is the review for our second test on forces. And the topics on there are forces, Newton's laws. So we're going to talk about balanced and unbalanced forces. We're going to talk about free body diagrams and being able to draw them well. And then from those free body diagrams, telling if forces are balanced or unbalanced. We'll go through the examples with that, which are found on your review. Um, the specific forces of gravity, normal force, friction, and tension, and they'll be involved in a problem or two. Newton's laws, first, second, third, identifying which law is being most demonstrated in a situation. And then we'll finish up with centripetal acceleration and force. And usually that goes along with the Newton's law of universal gravity problem where something is going in a circle like a satellite. So on your review, the first part is drawing some pictures based on a situation. So we're going to draw a free body diagram, which is in this column, and I'll talk you through these answers. And then this column, the final column, is describing what's happening to are the forces balanced or unbalanced, and as a result, what's going to happen to the object in the motion. So in this object, number one, it says the object sits motionless. So if something is not moving, it's at rest, another way to describe it. So if we think about the forces, I drew a force of gravity going down and a normal force going up. And those two forces, um, because they are balanced, they are canceling each other out and is not accelerating. So when something's at rest, it's motionless, its acceleration is zero, the net force is zero, and that all means it's balanced. So nothing's happening here. The two forces, the upward force of the ground pushing up, which is the normal force, is canceling out the gravity force, which is the earth trying to pull down. So the object slides across a frictionless table at a constant speed. The wording here that's really important is constant speed. So if something's going at a constant speed, that means it's not accelerating. That means the velocity is constant. So if, again, the acceleration is zero, the net force is zero, which means that the forces are balanced. So really the first situation and the second situation are the same free body diagram. So same picture here, we got gravity going down, normal force going up. And the only way we know that, like if we were just given this picture, we would know it's balanced, we would know the acceleration zero, but we couldn't say if it was at rest or if it was moving. All right. So now we have finally one where it is unbalanced. So it says the object slides across the table and friction and slows down because of friction. So slowing down means that the forces are unbalanced because there's a change in motion. So with the change in motion, that means that the net force is not equal to zero and the acceleration is not equal to zero. So there is an acceleration. So I just imagine like that box again that we had in the beginning was moving to the right. So it has some velocity going to the right here. We still have gravity pulling down. We still have normal force trying to push up, and they're canceling each other out. But the friction is slowing it down. So if the object is moving to the right, friction is going to go the opposite way to slow it down, which is to the left. And that's actually the direction of the acceleration. So our overall acceleration would go to the left, and our overall net force would also go to the left if our box was sliding to the right, like we have it in this kind of picture. Okay. So if those are like the motion lines where the box is sliding to the right, these both point left. Okay. Finally, it says a person pulls on the block so that it moves across the table at a constant speed. Again, constant speed means that the acceleration is zero and the forces are balanced and the net force is zero. So if that's happening, these things have to all cancel out. So friction is just going to the left like it was up here. Normal force is still up, gravity is still down, and the pulling force has to equal the friction force in order for it to be at a constant speed. So that's kind of overview of reviewing how to do free body diagrams and how you can look at free body diagrams and tell whether, based on the description and the situation, whether an object is balanced or unbalanced. And that's all about, does the motion change or does it not change? So the first problem review here is for this lawnmower problem. So I'm going to go through this. And this one, it might be a little more difficult than the one that you actually have on your test. So this one has an angle, and we reviewed vectors and a little bit of that earlier in the course. But you just have to read carefully and just make sure you understand what's going on. We're in this problem; it does require a little bit of vector math and trig to figure out the components of this pushing force. But If you don't have that, like if it just says it pushes horizontally, then you don't have to worry about the cosine and sine part. You just got to fill it in the table, right? So this one reads, you push your 15-kilogram lawnmower, underline, across the lawn. You push along the handle of the lawnmower, which is inclined at 35 degrees, with a force of 120 newtons. The coefficient of kinetic friction is 0.35, and we're supposed to determine the acceleration of the lawnmower. So the first thing you should do is draw your free body diagram. So this dot represents our lawnmower here, and kind of just retracing this, we're pushing the lawnmower kind of down and to the left. If you imagine how you would push this lawnmower, that's what's going on in this. So you're pushing down to the left. That means it has two directions. It's got an X component, which is maybe going across like this, and it's got a Y component, which would be kind of pushing downward on our object, something like that. So that's that overall like force that you're applying through the handle of the lawnmower. The lawnmower has a mass, which is 15 kilograms, so that's M. So that's going down here. That's the force of gravity. It says that there is friction, so friction is going to go the opposite way to the way that it moves. So if we're pushing down to the left, we expect the lawnmower to kind of have a velocity going this way. So if the velocity is going that way, friction is going to oppose the velocity. So I drew friction going kind of horizontally to the right here. And then the other thing that's acting on it is the ground. So a lot of times people mess this part up. The ground and the normal force, they are not equal in this one because the ground has to push up more. So this force going up that I just drew on the screen is bigger than this individual gravity force going down because we're pushing. So these two added together are canceling out this. The normal force is canceling out both of these. So if you weren't pushing down, if you were just pushing across, these would be equal because you can tell that it's not accelerating up or down. But because you are pushing at this kind of down and to the left situation, this normal force has to be bigger. So it tells you 35 degrees, that's theta, that's the angle of the force that you're applying. And the amount of force that you're applying is this 120. So that's like the push, okay? And then this coefficient of friction, that's the U symbol, and it's moving, so it's kinetic. All right. So we're going to go through and just calculate the different ideas, but remember, once you've drawn your free body diagram, these are the things you got to figure out and combine. So that's what this chart's for. So we need to figure out gravity, the friction force, the normal force, and the pushing force overall. We know the amount, but we're going to break it into the X and Y components because we got a situation where it has more than one. So coming back over here, I use the gravity equation, G equals mg, to figure out how much gravity is pulling down. And looking at my chart and this free body diagram, gravity, G isn't going left or right. So it's got a 0 here in the X component, and it's going down, so I have a negative in the Y. So again, most of the time I recommend you go through and look at these arrows and figure out which way they're going, right, left, up, down, and base your positive or negative or zeros on that. So gravity is 0 and negative in the Y. The pushing force has two components. It goes left and down. So left is negative in the X, down is also negative in the Y. So that's why I have a negative and negative here. For the friction force, or sorry, for the normal force, that's just going straight up. So it's 0 in the X because X is horizontal and it's positive in the Y. And then finally, the friction force is going to the right. So that's a positive here on this image, and it's not going up or down, so that's 0. So I got 0, 0, and positive, negative, or sorry, 0, negative, 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 0, positive, positive, 0. So then we're going to fill in the numbers. So I already did this work and showed it up here. So 15 times 9.8, that's 147. That's M times G, or the gravity. So that's a negative 147 here. We're going to calculate the components of the pushing force. So the arrow going to the left is 120. And you would hit 120 cosine of 35 in your calculator. And make sure, again, you're in degree mode. Make sure you're putting in the calculator the right way. And that'll get you 98.3 for that. And it's going left, so that's why it's negative. Similarly, we're going to find the push in the Y, which is 120 sine of 35. So again, it's the amount of force times the cosine or the sine of the angle. And again, cosine generally goes with X and sine generally goes with Y. That's how it'll be. If you have any with those on the test, which you might not, like it just says pushes horizontal, just make it go in the X. So you get those values. And if you didn't get those values, you probably have something, either you're entering in your calculator wrong, or you've put it maybe in the wrong mode. So make sure you're in degree mode. So if you look at the boxes that I've filled in, I filled in this row and this row. We know friction here is 0, and this lawnmower is not going to like accelerate upward or downward. So I could fill in this 0 as well. So really this box is the empty box, and we're going to use like basically the idea that the normal force is canceling out these two that are going down. So these two going down, when I add them together, I get this value of 215.8. And that is the amount of force that the ground has to push upward. So that's the normal force. And then once we have that normal force, we got that column figured out, and I know the coefficient, I can solve for the friction force, because I'm just using the fun equation, F equals coefficient times normal force. So 0.35 times 215.8 will get you 75.5. Finally, you're going to add up this X column to get this bottom box. And if you add negative 98.3 and a positive 75.5, you get a negative 22.8. So that is the net force. That is the overall amount of force acting on the object. And then we're going to take that and use it with the net force is equal to the mass times acceleration, and solve for the acceleration, because that's what it wants here at the end, calculate the acceleration of the lawnmower. So when we do that, if I plug in negative 22.5 for the net force, the mass we said in the beginning was 15. So I have those two numbers, and acceleration is what I'm looking for. And you just divide through by 15, and you should get 1.52 meters per second squared. Missed that little squared thing. So that should be there. And it's going to the left. And that makes sense, because that's what's happening to our lawnmower. Like as we push it, it is speeding up as we move to the left. So you'll have a situation where you have forces acting on an object, and you're going to have to do this kind of work. Again, on your test, I don't think I make you do this X and Y part. So unless it has an angle, don't make up an angle. Make sure you understand what these different values mean when you read your own problem on that assessment. All right. So then we're going to get into some of the other kind of conceptual ideas that you had to do. So you had to figure out, we talked about Newton's third law, Newton's laws, and the third law is the one with action-reaction pair. And you're going to have to identify an action-reaction pair in a situation. So I'll give you some sort of picture like this, where a ball is maybe moving and it's going to fly and hit a glove. And it says state the action-reaction pair when the player catches the ball. So the action-reaction pair would be the interaction between the ball and the glove. So those are our two objects. So the ball is an object and the glove is an object. And in the lessons before, I've described this as caveman talk. So it's like one thing pushes or pulls on another thing, and then the opposite happens. Like you switch the nouns and you switch the direction. So I'm going to say the ball pushes the glove to the left, because the ball's moving, it's going to go and hit the glove. So that's my statement. The ball pushes glove to the left. And then the reverse of that is the reaction. So the reaction would be you trade, or you switch and flip. So the glove is going to come first in the statement. So the glove pushes the ball, and it pushes it in the opposite direction. So if this one is left in the action, the reaction, the glove is pushing back to the right. And that makes sense, because the ball is going to push on the glove and make it accelerate in the direction it's moving. And the glove pushes in the opposite way. And because it's the opposite way the ball moves, it slows down. So that is the action-reaction pair in that situation. So you'll have something similar to that. So you just have to identify the two objects. So two objects or nouns in the situation. Also make sure you are aware of, like, do you think it's a push or a pull? It's just one. This verb never changes. So if it's pushes in the beginning, it's going to be pushes at the end. If it's pulls in the beginning, it's going to be pulls on the end. And then two objects and the directions. So the one is either pushing or pulling left or right or up or down, or forward or backward, however it's worded, what it looks like in the picture. And then you just switch them. So if the one is pushing one way, the other is pushing the exact opposite way. All right. Continuing on with Newton's laws, I gave you these to kind of practice to decide which law you think is being exemplified in this situation. So this one says a frog leaps upward off its lily pad, is pulled downward by gravity, and lands on another lily pad instead of continuing on in a straight line. So that goes along with the first law, which is an object rest stays at rest, an object motion stays in motion unless it's acted upon by a net force. So the force of gravity is the net force acting on this, and it makes it change its motion. So that's the first law. The second one, as the fuel in a rocket ignites, the force of the gas expansion and explosion pushes out the back of the rocket and pushes the rocket forward. So this one is the third law example. So the gas pushes out the back of the rocket. So the rocket kind of, if I draw a really rudimentary rocket, here we go. So like little rocket here. And if you imagine this is the exhaust coming out the back. The rocket exhaust pushes the rocket forward. So the gas here, this red stuff that I'll have, that's like the fire shooting out the back, that pushes the rocket forward, and the rocket pushes the fire back the other way. So that's the action pair. Again, back and forward, that would be my hint in this to make me think of the third one. Standing on a train, the subway suddenly stops, and your body continues to go forward. That's a first law one again. So it's like you're moving if you're on the train, and I'll draw a real basic like subway train. So if you're standing in a subway, I don't know if you've ever had this experience, and hopefully you haven't, because it would maybe be scary. If the subway car suddenly stopped before you were moving with the subway car, because the car is moving, so everything's moving at this velocity, and suddenly if that subway car suddenly stops, your body wants to continue moving in a straight line at the same velocity, and that is Newton's first law. The second one is the easiest one probably to identify. So it says after you start up your motorbike, as you give it more gas, it goes faster. So Newton's second law is this idea of like the equation, either F equals ma or A equals the net force divided by m. If you are looking at how things, the acceleration of the object is changing in some way, that is going to be a second law. So as you start up your motorbike and give it more gas, so as you give it more gas, you imagine a motorcycle and give it more gas, you're increasing the force acting on that motorcycle. And when that happens, it goes faster. So if the net force increases, the acceleration is also going to increase. It also could be something with the mass. So like if you applied the same force to two different objects and the masses were different, they're going to have different accelerations. So if it's any relationship with F equals ma or A equals F over m, that is the second law. Okay. And you're going to have a situation where you're going to have to pick out which law you think is the best one, or which one is being demonstrated the best. All right. A couple more ideas. This one is dealing with kind of our centripetal force and Newton's law of gravity idea. So it says a satellite is in circular orbit around the Earth. For each of the changes listed, tell whether the force would increase, decrease, or stay the same, and explain. So really, you have to look up here at this equation. So this equation is Newton's law of gravitation. So Newton's law of universal gravitation, big G, m1, m2 over r squared. Big G is a constant, so that doesn't change ever. M1 and M2, those are the masses. We talked about this in the simulation last week, but going through it again. R is the separation between the two things. So if we had like the Earth, I'll just put an E for Earth here. It's blue, so that sort of works out. So that's the Earth, and maybe we have a satellite out here at some distance away. The distance between the center of the Earth and the center of the satellite, that red dot, which is our satellite, that is the R value. So that is how far they are separated away. Each one has a mass, and it says if the mass of the satellite were less, the force would what? So if it doesn't matter what you call M1, M2, but let's say M2 is the satellite. If that gets smaller, if you look at that equation mathematically, if that gets smaller, the gravity is going to get smaller. So that is the idea. So less mass means less gravitational force. The second one says if the mass of the Earth were more, so somehow we've made the mass of the Earth get bigger. So maybe M1 was the mass of the Earth. So if this value increased somehow and everything else stayed the same, that would make the force of gravity get bigger. So that's the A and B. And then the satellite part, it says if the distance between the satellite and the Earth was increased, the force would do what? And it's decreased because they're inversely related. So again, you should have seen this relationship in that simulation lab you did with universal gravity. But as you get things further and further away, there is less and less force between them. So that would make sense, right? So like if you imagine you were in a science fiction movie and you're on Earth and you weigh something on Earth, and as you move further and further and further, you get really far away from the Earth, your gravity, the force attracting you to the Earth gets smaller and smaller and smaller. Okay. So so that's dealing with mostly the gravitational idea. And then the next problem that we're going to do deals with the FC and centripetal force and things like that. So this problem reads, if a loop of a roller coaster, in the loop of a roller coaster, a centripetal force acts on a 60 kilogram rider, so 60 kilograms, that's a mass again, to maintain a circular loop. Velocity of the rider is 15 meters, or I'm sorry, 14 meters per second, and the radius loop is 20 meters. And we want to calculate, find the centripetal acceleration of the roller coaster, and then find the centripetal force acting on that rider. So, and then finally, in what direction is the force always point? So for A, the centripetal acceleration is v squared over r. The velocity is the 14. The radius is the loops is 20. So 14 squared, which is 196, you're going to divide that by 20, and you end up with 9.8 meters per second squared. So that's it. For part B, excuse me, it says find the centripetal force acting. So centripetal force is just a specific version of net force. So M times A, and if it's centripetal force, it's centripetal acceleration. So you're going to take 60 and multiply it by this 9.8, and you get 588 newtons for that one. And for part C, centripetal means center seeking, so it is always towards the center of the circle. So that is the answer to the last of those questions. Okay, so we've gotten through that review. Hopefully that is helpful, me like talking through it a little bit. You can find all the images for all the review answers on D2L. So good luck on your test, and I will talk to you next time.